Okay, welcome back. Let's get started. Today we are right here, class number 13, lucky number 13. This is day 2 of applications of systems. If you recall, last class, which was a while ago now because of the Monday holiday, we did a bunch of word problems like chocolate bars and sweaters, and we made tables and we created 2 equations in 2 variables, and then we used either substitution or elimination to solve those equations. Today, it's the same idea. Same tables, same process, 2 equations, and then substitution or elimination. The word problems from today are typically a little bit harder than the word problems from the previous class, but it's the same techniques. Looking ahead on Friday, we have our review day for test number 1. Nothing new on that day. Then on Monday, coming up, test number 1, which covers the material from lessons 1 through 13. Again, today is lesson number 13, and so at the end of today, we will have reached the end of the material for the test. But the test is on everything from the entire semester, starting with the first day and going through today. Okay? It is not too early to start studying for Monday's test. You got the whole practice problems packet. You got the big packet we've been working on with all the activities and maybe some even more practice problems if you haven't gotten there. You got old homeworks, you have old quests, you have homework problems I never assigned from the book. Lots of resources for these for the test. Okay? All right, so let's jump in here on page 102. So today, the application problems will involve mixtures using percentages and travel. Here we go. Number 1, antifreeze is a mixture of the chemical glycol and water. Let's pause right there. If you get a bottle of antifreeze, you go buy it from the mechanic or from the auto parts store. There are 2 ingredients in that bottle. Glycol, which is a chemical, and then water. Those are the only 2 ingredients. I don't know, then a color blue or something. All right, so that's what the word antifreeze means, okay? It's this combination of 2 things. So the next sentence says, an auto mechanic keeps bottles of antifreeze in 2 strengths. The first bottle is 20% glycol and the rest is water. Let's pause. 20% glycol. So you got this big jug of thing called antifreeze. Some glycol, some water. 20% of that jug is glycol. The other 80% is water, okay? And the basic idea with all of the mixture problems, starting with this one and going through the activities, is that you're going to have like a whole, and then you're going to be focused on a certain percentage of it, and we'll call that the part. And the part in this case is the glycol. The whole is antifreeze, the part is glycol. The second bottle that the mechanic has is 35% glycol. The rest is water. The 35% one is more concentrated, right? It's your concentrations we're talking about. So what this mechanic is going to do is going to mix some of the 20% and some of the 35% before we read what the goal is. Suppose we mixed equal amounts of the 20% and the 35%. Would you guys buy that the percentage of glycol in the mixture is just halfway between 20 and 35? Oh, we don't buy that? I want us to buy that. I think it's true. If you use equal amounts of like the 20% stuff and the 35% stuff, the thing at the end of the day, I think, is going to be right halfway between 20 and 35, 27 and a half. I think so. If you use more of the 20% stuff, then the percentage in the mixture will be closer to the 20, right? Like I can pull the percentage close to the 20 by using mostly 20. Or if I use more 35, then I can pull the percentage up, all right? But do you guys buy that I can get any percentage I want between 20 and 35 just by using the right ratio of these 2 liquids? Okay, so here's the goal. The mechanic needs to create 12 quarts of antifreeze. That's the whole. That's the glycol and the water together. We want 12 quarts of this stuff, and I want it to be 25% glycol. That's the concentration we're after. And 25% is at least in the game because it is between 20 and 35. All right? So the question is, how much of each should we use to build this 12-quart mixture with exactly the right concentration? We're on page 102. Okay, so we use our, we got to define variables first. The question again is how much of each bottle should be in the mixture. So we'll let L be the number of quarts of the 20% concentration antifreeze. Is that the whole or the part? 2 votes for part. The amount of antifreeze, is antifreeze the whole or the part? Antifreeze is the whole. Yeah, the 20% is just the part, okay? But L is the whole, the entire liquid, including the water. H for high, the amount of antifreeze in quarts in the 35% concentration. Let's start filling in. So I'm going to point out one thing that I didn't write here, but this column is going to be the whole. This column right here, well, it says it, but I'll write it up here, is the percent. And this column over here is the part. That's going to be the order for all of these whole and part problems. The whole goes first, then the percent, and then the part that we're focused on. So let's fill in some of these numbers. So first, the percent column is usually the easiest. What number am I putting in the first row? 0.20. And it was good to not say 20, right? We got to convert those percentages to decimals when we put them in the table. Okay, the next row, I guess that's 0.35. Now, in all the problems in our last class, this last row right here in the middle was blank. We didn't put anything there, but I think we got to put something here. Because the final mixture, we have a desired percentage. What is it? It's 25%. So we put a 0.25 there. We're not adding. You know, usually we add in that total row at the bottom, but not here. Okay, next up, first column. These are our variables. The amount of antifreeze. What letter did we use for the 20%? That was L. This one right here is H. Okay, that's the whole antifreeze. Glycol plus water. There is a number for the final mixture. How much antifreeze do I want at the end of the day? I want 12 quarts. So we put a 12 there. And hopefully we can see one of our equations is going to come from that column. What is it? L plus H is 12. That's the whole, right? That's not the glycol part. That's the whole. Okay, let's come over here. We're going to start in the bottom right. I want to know how much glycol is in each of these different rows. This is the part. Okay, let's look in the bottom row. I've got 12 quarts of antifreeze. That's the whole. 25% of that stuff is glycol. So how many quarts of glycol do I have? It's 3. It's 25% of 12. Yes? It's a quarter of 12. And so I really want us to understand that multiplying those two numbers is the right thing to do. Of the 12 quarts of antifreeze at the end of the day, 3 quarts are glycol. What are the other 9 quarts? Water. That's it. Just a quarter of it is glycol and the rest is water. So this last column is going to be the glycol. And to get the last column, we just multiply the first 2 columns. That's what we did over and over again on Friday's class. 12 times 0.25, that was just that number. 0.20 times L, and then 0.35 times H. Okay, and the second equation comes from this last column. It's the glycol column, it's the part. You got 0.20 L, that's how many quarts of glycol from the first mixture. 0.35 H is how many quarts of glycol from the second mixture. And then we smush them together and we add them up and we're hoping to get 3 quarts of glycol at the end of the day. And so that's that equation right there. Any questions on that one? Okay, so we're not going to spend our time solving it, but here you would either do substitution or elimination. Feel free to multiply everything by 100 if you want to get rid of all those decimals. There is an answer written down. Looks like it's 8 quarts of one and 4 quarts of the other. You can check that if you want more practice solving systems later on. But we are going to move on to number 2. We'll set this one up. A similar approach can be used for problems involving distance, rate, and time. For all such problems, we will use the formula rate times time equals distance, or R times T equals D. This is a formula that you all believe. It's one that you all know, even if you don't recognize it with these letters. But if I tell you I drive 60 miles per hour for 3 hours, what can you do with those 2 pieces of information to give me something new? You can multiply them, and what will that tell you? 180 what? Is it miles per hour? Right, just miles. 180 miles. You multiply those two things, tells me how far I went. So that's the formula. Rate times time equals distance. 60 miles per hour is a rate. 3 hours is the time. Multiplying them is something very natural for us, and it gives us the distance. So let's see if we can apply that formula to a brand new kind of problem. Irma flies her plane with the wind and makes a 450-mile trip to Saratoga, New York in 3 hours. The return trip against the wind takes 5 hours. We want to find the speed of the wind and the speed of the plane in still air. Okay, so the idea here is that planes have like a certain speed limit, some maximum speed that they can travel if they floor it. I don't even know if that's the right phrase for planes, but if they gun it and give it everything they've got, the plane has a certain speed that it can travel and it cannot go any faster. But if the wind is at the plane's back, then the plane actually will travel faster than it normally would be able to because it is being helped by the wind. And if the wind is facing the plane, then the plane is going to go slower than it normally would in still air because it's fighting against the wind. And if you've taken any trips across the country, I forget which direction is faster, but typically, like if you go from like here to the West Coast, like one direction is like an hour less than the other. I mean, it is significant because of the wind. So we are going to assume that the wind is a constant speed all the time, pointing in the same direction all the time, which is certainly a simplification, but we need to assume that to do the problem. So the question says clearly what our variables should be: the speed of the wind and the speed of the plane in still air. Always got to have units. In this case, our speeds are miles per hour, but the speeds could be different units than that, right? Could be like meters per second or feet per hour, lots of different things. Just look at the givens in the problem. Okay, let's start filling in. We'll fill in the times first. The trip to Saratoga was with the wind. How long did that take? 3 hours. And against the wind, 5 hours. So far, so good. Now we need to fill in the first column. Now, don't write this, but in the past, pretty sure in every other one of our tables, the two variables went in the first column. Don't put that. But that's what always goes in the first column, right? L and H was up above. Okay, so let's figure out what it actually should be. Suppose, I'm just going to make up an example here. Suppose that the speed of the plane is 100 miles per hour. That's with no wind. That's like its normal ability. And suppose that the wind is 20 miles per hour. And suppose for a second that the plane and the wind are going in the same direction. The wind is helping. How fast would the plane actually go? Normally the plane goes 100 miles an hour, but it gets a 20 mile per hour speed boost because of the wind. So 120, right? We just add them up. And how fast will the plane go when it is fighting against the wind? 80, right? It loses 20 miles per hour from what it normally would do. And so if I'm writing formulas over here, expressions, well, let's see, with the wind, I guess I'm just adding them up, right? P plus W. Plane plus the wind. And if we are fighting the wind, it is P minus W, 100 minus 20, page 102. Okay. And so for every one of these kinds of problems, it's going to be P plus W when you're going with the wind, P minus W when you go against the wind. I could change the problem a little bit. I can make it a boat. What about a boat in a river? What takes the place of the wind? The current, right? You can have the current helping you in one direction and hurting you in the other direction. When it helps, it's a plus. When it hurts, it's a minus. That's always what goes there. Okay, let's figure out the last column. Here is our new formula. Rate times time equals distance. And hey, look, the first column is the rate and the middle column is the time. So what should we do with those to get the distance? We should multiply them, which is exactly what we've been doing in all of these tables for 2 classes now. So it's kind of interesting that we can solve like a really wide range of problems using the same format, multiply the first 2 columns and get the last column for different reasons. Okay, so then here I will put 3 times P plus W, throw that in parentheses. and then 5 times P minus W. And these are the distances, but actually the distance was given as a number in the problem. How far was this trip? 450. So on the one hand, 3 times the quantity P plus W equals 450. That's one valid equation for us. And the return trip had better be exactly the same 450 miles, so 5P minus W is also equal to 450. So we get our two equations there. Again, we're not going to solve them. I'm just focused on the setup for these new problems, but you'll solve during the activities. But I want to point out number one, in order to solve these two particular equations, one technique would be to distribute, right? 3P plus 3W equals 450, and that's fine. And then you can proceed either elimination or substitution. But the really smart way to solve these problems is to actually divide both sides of that first equation by 3. If you do that, the 3 goes away on the left-hand side. 450 divided by 3 is 150. That is a much friendlier equation because there are 1s in front of the variables. What can I do to make the bottom one more friendly? Divide by 5. P minus W equals 5 into 450 is 90. And these two equations are perfect for elimination because if you add them right now, what happens? The W's go away. So you don't even have to multiply the equations by anything, right? It's already set up that way. Certainly you don't need to do that, but I wanted to point it out. Okay, 2 common mistakes I've seen with these travel problems from students. One common mistake is suppose that instead of P plus W, we put W plus P. Is that okay or is that wrong? That's fine. Still the same value as P plus W, right? Suppose that we put W minus P. Is that okay or is that wrong? That's wrong. And if you did W minus P for the 100 and the 20 that we picked before, what would you get? Negative 80 miles per hour. That is not what the plane is doing, and you will not get the right answer if you solve that equation. But there's nothing going to jump out at you that says this is wrong. Like, you just have to know the plane is the thing that goes first. You are not subtracting the wind minus the plane. You are doing plane minus wind. So be careful about the order. Got to start with the plane. Okay, the other common mistake I've seen is this. The students sometimes will put the time in, like they won't think about where the time goes, and it feels like it shouldn't matter, right? Like it's just 5 for one trip and 3 for the other trip, and if you change the row headings, you know, whatever, it's fine. But the problem here is that P plus W assumes that the wind is helping the plane, yes? And if the wind is helping the plane, is that going to take more or less time? Less time, but we have put the more time number up there. The 5 hours cannot possibly be matched up with the P plus W. So you got to make sure, like it doesn't matter which row is which, but you got to make sure you are putting the faster time with the faster speed. Okay, any questions on that? Okay, so let's move on to the activities. Yeah, so same directions as the other day. I don't want you to solve them first. I want you to fill in all the table, column headings, row headings, all that stuff. Define some variables, write 2 equations. Once you have 2 equations written down for problem number 1, move on to problem number 2 and write 2 equations. Once you've got 2 equations written for all 5 problems, then go back and start practicing solving them, substitution or elimination.